In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about does black hole continuum spectrum signal higher curvature gravity in higher dimensions. It was written by Indrandi Banjir with the School of Physical Science in the Association for Curvature of Science. Extra dimensions, which led to the foundation and inception of string theory, provide an elegant approach to force unification. With ball curvature as high as the Planck scale, higher curvature terms, namely F or gravity, seems to be a natural addendum in the bulk action. These can not only pass the classic tests of general relativity, but also serve as a potential alternative to dark matter and dark energy, with interesting implications in inflationary cosmology, gravitational waves, and particle phenomenology. It is worth exploring the impact of extra dimensions and higher curvature in black hole accretion. Various classes of black hole solutions have been derived which bear non-trivial imprints of these ultraviolet corrections to general relativity. This in turn gets engraved in the continuum spectrum emitted by the accretion disk around the black hole. Since the near horizon regime of supermassive black holes manifest maximum curvature effects, we compare the theoretical estimates of disk luminosity with quasar optical data to discern the effect of the modified background on the spectrum. In particular, we explore certain class of black hole solution bearing a striking resemblance with the well-known Resenian Nordstrom de Sitter or anti-de Sitter flat spacetime, which unlike the general relativity can also accommodate a negative charge parameter by computing error estimators like chi-square notch Sutcliffe efficiency index of agreement, and etc. We infer that optical observations of quasar favor a negative charge parameter, which can be a possible indicator of extra dimensions. The analysis also supports an asymptotically the Sitter spacetime, which an estimate of the magnitude of the cosmological constant whose origin is solely attributed to higher curvature terms in higher dimensions. Now I want to go through the introductions. The general relativity or GR is a classic example of a scientific theory that is elegant, simple, and powerful. Till date, it is the most successful theory of gravity in explaining a plethora of observations, namely the perihelion precession of Mercury, the bending of light, and the gravitational redshift of radiation from the distant stars. To name a few, the reference 1 up to 3, recently the shadow of the black hole in MX87 observed by the Event Horizon Telescope has further added to its phenomenal success. Yet it is interactive to subject general relativity to further tests since it is marred with unresolved issues like singularities and falls short in explaining the nature of dark energy and dark matter. Moreover, the quantum nature of gravity is still elusive and ill understood. All this makes the quest for a more complete theory of gravity increasingly compelling, such that it yields the general relativity in the low energy limit. Consequently, a surfeit of alternate gravity models are proposed which can potentially fulfill the deficiency in general relativity. A viable alternate gravity theory must be free from ghost modes, be consistent with solar system based tests, should not gender a fifth force in local physics, and should successfully explain observation that general relativity fails to address. The alternate gravity models, which fulfill this benchmark, can be broadly classified into three categories. The first category is modified gravity models, with the gravity action is supplemented with higher curvature terms. For example, FR gravity, Lang, Source, Lovelock models, and etc. The second one is extra dimensional models that alter the effective four-dimensional gravitational field equation due to the bulk Rayleigh stresses and higher order corrections to the stress tensor. The third one is scalar tensor theories of gravity, which includes the Brans-Dicke theory and more general Horensky models. In this work, we will consider modifications to the gravity sector by introducing FR gravity in five dimensions. Among the various modified gravity models, FR theories have attracted the attention of physicists for a long time, since they invoke the simplest modification to the Einstein-Hilbert action and yet exhibit sufficient potential to address a host cosmological and astrophysical observation. These include, but are not limited to, the late time acceleration and the initial power law inflation of the universe, the four cosmological phases, the rotation curves of spiral galaxies, and the detection of gravitational waves. All of these models are plagued with the ghost modes. Certain FR models, for example, FR theory on a constant curvature hypersurface, can be shown to be ghost-free. In addition, they can successfully surpass the solar system test, which only impose constraints in epsilon r and hence on the model parameters. Extra dimensions, on the other hand, were mainly invoked to provide a framework to unify gravity and electromagnetism. They subsequently provided a framework for string theory and M theory that succeed in unifying all the known forces under a single umbrella. The large radiative corrections to the Higgs mass arising due to the huge disparity between the electroweak scale and the Planck scale led to the emergence of a diversity of string-inspired brand-word models. Most of these models assume that the observable universe is confined in a three-brane where all the standard model particles and fields reside, while gravity parameters are to the bulk. They possess interesting phenomenological implications and distinct observational signatures, including production of mini black hole, which can be tested in present and further collider experiments. In the galactic scale, they offer an alternative to the elusive dark matter, while in cosmology they have interesting implications in the inflationary epoch and also serve as a possible proxy to dark energy. Since the ultraviolet nature of gravity is known, it is often believed that in the higher energy regime, this deviation from Einstein gravity may manifest to existence of extra dimensions. And moreover, the bulk curvature is expected to be as high as the Planck scale, and hence higher order corrections to the gravity action should become relevant in the higher energy regime. In this work, we consider a single band world scenario with a positive tension, which is embedded in a five-dimensional ball containing FR gravity. The addition of high curvature terms in higher dimensions cause substantial modifications to the effective gravitational field equation on the brain, which are obtained from the Gauss-Kodazi equations and junction conditions. Such deviation from the Einstein equations are expected to become more conspicuous in high energy, high curvature domain. Therefore, the near horizon regime of black holes, where the curvature effects are maximum, seem to be an ideal astrophysical laboratory to test these models against observations. Various classes of vacuum solutions of these field equations have been obtained in references 28, 29, 32, 97, 98, which possess distinct signatures of extra dimension of our gravity. In the event the vacuum solutions are static and spherically symmetric, the electric part of the Weyl tensor can be decomposed into terms of the involving dark radiation and dark pressure. Suitable integrability conditions lead to different classes of vacuum solutions which determine the space-time geometry. The solution thus derived exhibits substantial modification from the well-known Schwarzschild spacetime, which are attributed to the non-local effects of the bulk Weyl tensor and the high curvature terms in action. These deviations in the background spacetime are sculpted in the continuum spectrum emitted from the accretion disk around the black holes. In particular, since the curvature effects are maximum in supermassive black holes, the quasar continuum spectra can act as potential astrophysical probes to establish, falsify, constrain these models. In a recent work, we explore exact black hole solutions in the brain with the bulk and Einstein gravity. It resembles the well-known Reisner Nord Stream space-time in general relativity, where the tidal charge parameter can assume both signature by comparing this luminosity of quasars in such a background with the corresponding observations. We conclude that the negative charge parameters is favorable, which is characteristic to Brandwood black holes. Adding our gravity in the bulk action adds the vacuum energy to term to the aforesaid black hole solution, where the cosmological constant owes its origin to terms involving high curvature and high dimensions. In this work, we investigate the effect of such a spacetime on the quasar continuum spectra, which enables us to explore the signature of the tidal charge parameter in the presence of the cosmological constant terms in metric. Subsequently, we also derive constraint on the magnitude of the cosmological constant from the quasar optical data. Further, we also investigate the effect of the other black hole solutions on the quasar continuum spectra, which are derived by altering their relations connecting to the dark radiation and dark pressure. The paper is organized as follows. In sections 2, we discuss the modifications induced the gravitational field equations due to the presence of bulk or gravity, the static spherical symmetry, vacuum solutions. Two of these field equations are reviewed in section 3. In section 4, we examine the properties of the black hole continuum spectra in presence of background spacetimes discussed in section 3. Section 5 is dedicated into numerical analysis, where the theoretical computed luminosity from the accretion disk of and the discussion of the hour results in section 6. Notations and conventions throughout this paper. The Greek indices denote the four-dimensional spacetime, and capitalized Latin alphabets represents the five-dimensional bulk indices. We will work in the geometry unit with G is equal to 1 is equal to Z, C, and the metric convention will be mostly positive. Before I go to the next chapter, I wanna describe these highlighted phrases and explain them theoretically and practically to understand this better in order to go to the next chapters.